there. I think you can go back later if you think of other things that you want to add to the course evaluation survey. I think you can circle back and add more comments later on if something occurs to you. Okay, so we've got the final on Tuesday, and we've already talked about this a little bit. I'm going to make it a comprehensive exam with more emphasis on recent material. I'll give you that same formula sheet that you've had before, along with the geometric formulas, table 10.1, if that's needed for a problem. You should bring your laptop with Excel. You're not going to need to do a water gems problem. There won't be a HEC-RAS problem on the final exam, but you should have Excel. And then when you use Excel on the exam, you have to start with the blank workbook, meaning that you can't use a previously solved homework assignment. You can't use a template file that I've provided. You're just starting from scratch. Does anybody have questions before we start talking about HEC-RAS? You may remember this previous example that we went through when we were talking about the direct step method. So this previous example, we broke the water surface profile curve up into segments, and we started here at a broad-crested weir where we knew the depth was 3.8, and we went upstream step by step and found out what was the length of the segment between two sections where we knew the depth. Like we said that we didn't want the water surface change to be any more than half a meter, and so that's how we figured out that there should be 6 segments. As we said, we know the water starting at 3.8 immediately upstream of the weir, and it's eventually going to get back to the normal depth. You know, if you get far enough upstream away from the influence of that choke, it'll be back to the normal depth, which we calculated to be 1.195. So it's getting shallower and shallower as you work upstream. And when we worked through that example using the direct step method, we only had 6 segments. And the more segments you've got, the more precise the answer can be, up to a point. You know, there is a point of diminishing returns where if you have 100 segments instead of 50, you're not going to get any more precise of an answer. But at 6 segments, there's still probably some opportunity for nailing it down a little bit finer. But this is just to refresh your memory about this particular example, because we're going to go through and solve it again the same example using HEC-RAS, just because we're familiar with it and we want to compare what kind of answers do we get with HEC-RAS compared to what we solved using that spreadsheet template and the direct step method. Now, HEC-RAS doesn't use the direct step method because remember, the direct step method is limited to channels where the geometry isn't changing as you work upstream or downstream. And if we want the flexibility to handle that, then we have to utilize the standard step method. And so that's what's the engine working in the background of HEC-RAS, is the standard step method. But here's what we're going to look at. This same 3.8 meter water depth upstream of the weir, and we have a rectangular channel. So here let's look at the geometry of the rectangular channel that's described. It's 7 meters wide, and the channel itself, we're going to say, has a height of 4 meters. And so just upstream of the weir, the water is up to 3.8 of the 4 meter height. So it's not spilling over the edges. We still have a little bit of headroom above that water. So we want to know in this example if we have a channel slope of 0.0015, and there's a flow rate of 15 cubic meters per second going through there. If we go 1,500 meters upstream, what's the depth at that location? So we're going to use the program to find the flow depth, a known distance upstream, and that could be a case where, you know, in the real world, if you've got the Ohio River at a certain location and you're measuring the depth with a stream gauge, a physical measurement of depth, you want to be able to calculate what will be the depth some distance upstream of where you're physically measuring it. So this is kind of one of those cases where we'd want to know what's the flow depth a certain distance upstream that's important to us. It could be that there's a road in that vicinity that's kind of particularly low and maybe vulnerable to flooding. It could be that there's a business or a home. So for whatever reason, we want to know the flow depth 1,500 meters upstream. And then the other thing we're going to try and figure out in this example is, if we keep going upstream, how far do we have to go until it's back to the normal depth? And that's what we answered in that prior example. In this prior example, we found the length of the backwater curve is 2430 meters. So that's how far we had to go upstream to find that it was back to the normal depth. In our example today, instead of saying how far do we have to go to get to the normal depth, we're going to say how far upstream do we have to go until we're within 1% of the normal depth. And now the reason for that is sometimes in numerical solutions, getting that last 1% of convergence can take really a long time, or it can be like an unrealistically long distance. It's kind of similar to, you maybe have heard the idea that, you know, if the wall is right here in front of me and I take a step half the distance to the wall and then another half and then another half and another half, I'll actually never get to the wall if I only ever go half the distance to get to the wall. And so it's not exactly that same situation here, but what we want to know is basically how far upstream until we get close enough to the normal depth that we're basically there. So at the location just upstream of the weir, this is what the channel looks like, and it's sloped upwards at this 0.0015. So we're also going to want to know at every location, like, what are the coordinates of the channel. We'll have to put that into HEC-RAS, kind of define how the coordinates are gradually sloping upward as we work upstream. So we know the critical depth and the normal depth from our hand calculations. And we're going to keep that in the back of our mind. Like, this is what we're looking for, is 1% of that normal depth. So basically, how far upstream do we have to go till the depth is 1.207 meters? Okay, so that's the setup. Now, that distance is what we're going to try and find. And the way we'll do it is dividing the channel up into sections of 100-meter steps. And then just see, as we work upstream from this location, which is our origin, this is going to be station 0. So we're going to be at station 0, then we're going to go 100, 200, 300, 400, 500. We're going to go all the way, like, we'll go of 3,000. Just hopefully that, you know, this depth of 1.207 meters is within that 3,000 meters, and if not, we can revise and continue making additional cross sections. So if we do go 3,000 meters upstream, we know that the bottom of the channel is at an elevation of 4.5 meters. So we're going to set an elevation datum such that the bottom of the channel just upstream of the weir, we're saying let's make this be 0 elevation. And then it's flat. A horizontal datum means that if we go upstream 3,000 meters, so 3,000 times the channel slope is how we get the z of 4.5 meters up there. And so what that looks like is, for our channel that's just upstream of the weir, these are the coordinates of the edges of the rectangular channel. So the reach station is starting 0 here and working upstream, and then the cross-section station is starting here at this location and working sideways. The station is what distance horizontally are we from that left edge. And we're not going to worry about, like, the geometry beyond the banks. I mean, in a real-world application, you'd want to know, like, what does the geometry of the floodplain look like? We're just going to only concern ourselves with this main channel for that example. Okay. So we've got our coordinates. This is the coordinates just upstream of the weir. These are the coordinates 3,000 meters upstream. And we're going to put it into HEC-RAS. So start HEC-RAS. Hopefully it's installed here. Yeah, it is. All right. Agree to the terms and conditions. We don't need the example project. All right. So right now you can see it's in US customary units. We're going to need to change that over to SI. So here in the options, unit system, switch it over to SI units. Okay. I want to set the project to SI. Yes. Okay. So now it says down here in this window that it is SI units. So we're good there. So let's start a new project. So file, new project, and it's prompting us to create a file name. And it's always a good idea to save your work in case the program crashes or in case you get distracted and walk away. So just browse to a location that you're going to be able to navigate to later. I'm going to create a folder that's just called RAS demo. All right, so I'm going to call this last Friday of the semester. All right, so when I do that, yes, I want to create a project. You can see here in this is just basically a list of the directories. The overall project has its name, and you can see it's got the file location, and then the extension is .prj. All right, so that's just kind of like the master file that all the other file names are going to be saved within. And next we are going to use this icon here, view/edit geometric data. So click, it's like a line with a couple of branches off of it. Click on that, and we're going to basically, this is a top view, we're going to draw a reach. So we're just telling it that from the top view there's some stream or river that we're going to try and model. So use this river reach button, add new river reach, and then we're going to click in two locations. One to start the reach, that's the upstream location, and then so click once and then move the cursor sideways. And this being a top view, it doesn't matter if it's high or if it's low or if it's horizontal. It has no physical significance. It's just like a schematic representation of a stream. And double click at the end to terminate. HEC-RAS has a lot more sophistication than we're going to just scratch the surface with today. You could have multiple rivers within a project, and each river could have multiple reaches. So we're just going to have one river that has a single reach. It doesn't have any tributaries that we're going to be modeling. We're just looking at a really isolated channel segment. So you have to give a name. We'll call it the river, and then the reach, only reach, because there's only one reach in this. So we name it. It would maybe be more important. You could be naming it, like Ohio River, Mud River, and like Little Cabell Creek, and so on. Its tributaries. But now that we've got a reach defined, we need to add some cross sections. We have to basically make a trough. Water's going to be flowing downhill through some channel, and so far the program knows, okay, there is a channel, but it doesn't know how wide it is or what elevation the bottom of the channel is at. We need to define that basin that the water is going to be flowing downward through. So click on the cross section button, and then we're going to add a new cross section. Here under options, add a new cross section, and we need to tell it the station for the cross section. And so the first station we're going to do is at this location. So you can see river station starts here at 0. So the station I want to put in is at station 0. Okay. I'm going to tell it the shape of the channel at that station. So I'm going to put in the coordinates using this. So I could give it a description like just upstream of the weir. Okay, so station 0, there's elevation 4. Station 7 is, oh no, I want to do also station 0, elevation 0. Station 7, elevation 0, and station 7, elevation 4. So those are just like the coordinates that's defining this rectangular channel. And let me define the n values. In this example, the n values in the problem statement say it's 0.02, left of bank in the channel 0.02, right of bank 0.02. We're not actually going to be outside of the banks, but I don't know if we'd get an error message by failing to define the n values. I don't think we need to define the lengths of the reach that's downstream of this location, because this location is going to be the end of our simulation. So we will define the downstream reach length when we go up to station 3000, but I'll leave this one blank for now. And now the left bank is at station 0 and the right bank is at station 7. And now with all of that entered in, I think we can click on Apply Data, and it's going to draw a little sketch of our channel. So you can see the bottom of the channel is at elevation 0, as we'd expect. You can see it's 7 meters wide, 0 to 7, so it's 7 meters wide. And if we go up here, the ground elevation is at 4, or that's like the banks are at 4. So I think this does accurately represent the cross-section we want to simulate. So we've got station 0 defined. Let's also define the geometry up at station 3000. So again, do options, add a new cross-section, and then at station 3000, we're creating a new one, and we can call this all the way upstream. They don't need names, but I think we can. It copied over the n value from the previous, just kind of as a default placeholder. Now, what's the downstream reach length? From this 3000 station down to station 0, it's 3000 meters left of bank, in the channel, and right of bank. We're assuming that this is like a uniform straight channel. It's not meandering. So the left bank length and the channel length and the right bank is all going to have the same distance. Okay, now we have to put in the coordinates. So here you can see what coordinates we're going to have. Station 0, elevation 8.5. Station 0, elevation 4.5. Station 7, elevation 4.5, and station 7, elevation 8.5. And then we have to tell it what is the banks at what station locations. And so again, the left bank is at 0, the right bank is at 7, and then we apply data and get a sketch showing the bottom of the channel is at elevation 4.5. Good. It's got a width of 7, and then the side slopes are vertical all the way up to 8.5. So this is an accurate representation. So now think about if we wanted to have stations like this every 100 meters, we're going to do this same thing 30 times. It would be really tedious to type in and actually to calculate what's the bottom of the channel at that location, what elevation are we going to have to manually key in. So rather than forcing ourselves through that tedious process of manually creating a lot of more cross sections, we can interpolate between the two that we've defined and just have it kind of linearly determine the channel bottom, and assuming that its shape stays the same because the width is 7 all the way through. So we can close this window and actually open up cross sections, because Close it. Tools, cross-section interpolation. Yeah, so what we're going to do is we're going to interpolate between two cross-sections, and upstream is 3,000, the 3,000 cross-section. Downstream is the 1,000 cross-section. And then what we're going to do is have a constant distance of 100 meters. So it's going to just basically find out at what altitude the bottom of the channel is at each of these new locations it's creating. So at 100-meter constant distance, I think if we click interpolate new cross sections, then you can see it's like kind of a front view of the whole channel and all the new cross sections it's created. We can flip between them just to make sure that it makes sense. So close it once you've interpolated, and let's look at the cross sections here. We're at 3,000 now, which is all the way upstream. And you can see the bottom of the channel is at 4.5, but here with these arrows, now we can toggle between what's the next one downstream. So at 2,900, so the bottom of the channel is at 4.35 meters. We can go downstream a little more, 28, 27, 26, 25. So it did a good job of interpolating for us. So that's consistent with what we've assumed in this example, that the slope is constant between the extreme upstream location and the downstream location. Okay, so I'll pause here for a second. Does anybody have questions, or is there any part that you need to see demonstrated again? All right. So let's save our work. We've defined the geometry, but we haven't saved the file yet. So click Save, and it's going to be prompting us to save geometry data as. So we got to come up with a name for the geometry of our defined channel. Let's just call it the river geometry. And you see the file extension is .g. So okay, it saved it, and then it looks like maybe it truncated here. The river geometry is the name. Oh, okay, but it's still using last Friday of the for the file name itself. All right, so we've defined the channel, but we haven't told it anything yet about the flow rate, and we also haven't told it what we do know about the depth. You know, we do know that the depth just upstream of the weir is 3.8. And so we have to tell it the flow rate going through here we want to simulate is 15 cubic meters per second. And then we want it to know the flow depth just upstream of that weir is 3.8. So that's our boundary condition, is forcing it to start with the depth at this location that it's known. Okay, so let's define steady flow data. So these buttons across the top, the one that we're doing is, it looks like a Q with a horizontal blue line above it. That means steady flow. So view/edit steady flow data. If you click on that, then what we need to define is the flow rate and the depth of the water at a location that we know it. So down here where it says PF1, you can see it says edit steady flow data for the profiles in terms of cubic meters per second. So click in this field and type 15. So we're telling it 15 cubic meters per second. And then we want to set the boundary condition. So options, reach boundary conditions. Yeah. So the reach boundary condition that we want to define is a known water surface. So click on known water surface, and so it says when the flow is 15 cubic meters per second, what is the known water surface? Oh, you know, I just realized I might be at the wrong location. So hold on a second. Yeah, this is at 3,000. I actually want to define the elevation of the water at 0. So let me I think I can delete this one, delete the flow data. Well, maybe I just choose at 0. Josh, how do I delete this one?
I don't think you can.
Yeah?
Because that was set.
Ooh. Okay, well, it's true. I mean, the flow rate's going to be 15 cubic meters per second at both of them, right?
Yes.
So 15 cubic meters per second here as well. And it is at the at 0 that I'm going to want to do the depth. All right, so reach boundary conditions. Yeah, downstream. Okay, so I may have been okay to begin with anyways. I don't know. Maybe I didn't need to specify the flow rate at 0 and at 3,000. But it's the downstream known water surface is 3.8. Okay. So here, yeah, I think I was all right to begin with. I was over-worrying myself. So here we've defined the boundary condition as a known water surface elevation at the downstream location, and the known water surface elevation was 3.8 meters. Okay. So let's close this and save again, and it's going to prompt us to save the flow data because that's some new information we've told it since the last time we saved. So I'll call this flow data. Okay. And then here we've got another row in the project manager telling me like where it's saved. By the way, we could take a look at that directory just to see if it's actually saving things. It was this RAS demo. So yeah, we've got some files in there. So now we have to tell it, do the calculations. So we've got a channel, we've got a flow rate, and a location where the depth is known. So now we're going to do a steady state run. So here on these little buttons across the top, it's this one. It's a person running on a flat ground. So that's your little reminder, your visual reminder. We're going to do a steady state run, so a steady state flow simulation, just with that known 15 cubic meters per second. So click on that. I think all we need to do, let's make sure it knows that it's subcritical flow. It is. It's subcritical flow. So if it had been otherwise, we'd need to inform it of that. But we got subcritical flow and compute. Okay. So let's pick through the results and see what happened. If we go to the cross sections, so we go back here to view/edit geometric data, and we look at the cross sections, now there's this blue stuff in there. It's water. There's water in the channel. So if we go all the way down to, for example, station 0, what did we know about the water depth at that location? It's 3.8. So take a look. Does it match what we had told it should be? Yeah, it looks like at this station 0, the water depth is at 3.8 meters. So it obeyed the boundary condition that we told it about. What if we go 3,000 meters upstream? Let's just jump all the way up to location 3,000. Okay. So the normal depth in this example that we solved, the normal depth was basically 1.2 meters. So does it look like the water's up to the normal depth here? So the channel bottom is at 4.5, and 1.2 above that would be 5.7. So yeah, it does look like the water's at the normal depth at station 3,000. But it was asking, what is the depth 1,500 meters upstream? So we could go there and look at the channel, just for the gee whiz view of it. Like here's at station 1,500. So here's the water depth, but we want to know precisely, not just like trying to get out a ruler and measure off of the screen like that. There's reports that we can get that'll tell us the depth and velocity and other flow conditions at each of these stations of interest. So here back in the main project menu, click on view this report. So the table on the left, view detailed output at cross-section, culverts, bridges, weirs, etc. So click that, and then here at the reach 1,500 meters upstream, it tells us the hydraulic depth is 1.77 meters. So, like we could go to 0, where we know the depth should be 3.8, and it does tell us, yeah, the depth at station 0 is 3.8. Or we could go all the way to 3,000, where we know it should be back up to the normal depth by then. So at station 3,000, the hydraulic depth, 1.20. So yeah, that's the normal depth. We're back, the water surface profile is working from, this is an M1 profile, so it's gradually getting shallower as you work upstream. But that location that we're interested in at 1,500, that location 1,500, the water depth, 1.77 meters. Okay, so that answers part A. What is the water depth 1,500 meters upstream? 1.77 meters. Great. We would have gotten a slightly different answer though, like if we only had 3 cross sections, like if we had a cross section at 0 and a cross section at 1,500 and then a cross section at 3,000, it probably wouldn't have said 1.77. There'd be some inaccuracies if you are stepping that far of a distance. It would have violated that kind of background principle that we've said, that you wouldn't want the water elevation changing more than about half a meter in a single calculational step. So keep in mind that the answer you get can sometimes be influenced by the number of cross sections you put into your simulation. I think 15 of them is giving us a good amount of precision between the start and this midpoint location. Okay, now part B. How far upstream until the water depth is within 1% of normal? So basically, how far upstream do we have to go till we see the depth is 1.21 meters? Because this isn't showing us 3 digits, it's only showing us 2. So we can toggle using this up arrow. So we're at 1,500 and it's 1.77 for the hydraulic depth. What if we jump up to 1,600? 1.67. All right, it's getting shallower. Keep going upstream until you find where is the location that our hydraulic depth is 1.21. There it is, at 2,600 meters upstream. So that's somewhat consistent with what we found when we used the direct step method. Different calculational method, and more importantly, different number of segments. We got 2430. Only 6 segments is kind of coarse, not as precise as we could be. This is more likely to be the true answer since we've divided it up into so many steps. We're probably not getting a lot of error within each section. But the answer to the question, how far upstream would you need to go until you're seeing the normal depth again? It's 2,600 meters approximately, and we're back to the normal depth, or within 1% of it. So that's HEC-RAS in a nutshell. This is what gets used in the real world for really sophisticated and complex natural waterways that you wouldn't be able to represent realistically in a spreadsheet, where the channel geometry is irregular and the width of the channel is changing at every single location upstream. It can do really pretty impressive things, and we've only scratched the surface of it, but I guess at a minimum you've now seen the program and have an idea of how it could be applied to the types of things that we've been solving manually till now. Okay, 11:41. I think I've held you over a couple times this semester, so now I'm paying back all that extra time that I've robbed from you. Let's just take one last look at these announcements. I guess the only other thing that you've got on your to-do list at this point is study for the final exam. And if you have questions as you're studying, I'd be happy to answer them. You can stop by my office or send me an email. And of course, all the lecture videos are also on YouTube. So if you really want to punish yourself, you could review those. So I'll see you Tuesday morning. Take care.